Hello everyone and welcome back. I'm Dr. Priya Hassan and this is our episode on astrobits. And today I'm going to talk about something which is very interesting, which people find very interesting rather in astronomy, and that is about black holes. So let's talk a little bit about black holes. Now, black holes are an enigmatic idea, and actually, it has been said that this is when God divided by zero, God actually came on to black holes. So, let's just talk about black holes. What is a basic black hole, and how is it formed? Now, in nature, you could actually have events or cases in which you have regions where the gravitational force is so strong, right, that nothing, not even light, can escape from it. Okay, and one of the ways we know that black holes is formed is by the formation of very massive stars. If a star is about 20 to 30 times the mass of the sun, then this star, as it evolves, the core of it then collapses to form what is called a black hole. Right? Let's ask our next important question about black holes. What is event horizon of a black hole? So the event horizon is actually in principle the point of no return around a black hole. So actually, if you look at this thing, this is the space-time, which has got distorted because the presence of the black hole comes in and it literally creates a hole inside where you have the singularity. And so what happens is this hole is in such a way that not even light can escape the gravitational force coming from this, and hence you get the name black hole. So the name black hole was actually given by John Wheeler, and but then it kind of caught on. So the singularity is basically the infinitely dense core at the center of a black hole where all the mass is concentrated. Okay. Do black holes move? Yes, black holes can move through space because they are going to basically feel the gravitational force from other objects. So, for example, you could have black holes merging because a black hole is reacting to the gravitational force of another black hole. You could have merging, or for example, if you have supermassive black holes at galaxy centers, these could also merge with other black holes. Next question is, can we see black holes directly? No. Black holes, like the name says, they are black because they are invisible, because light cannot escape them. However, what we do is we actually have what are called indirect observations. We look at regions around the black hole and we can use that to actually study the black hole. Next question, can black holes emit radiation, and if so, what is Hawking radiation? So most of you must have heard about Stephen Hawking, and Stephen Hawking proposed that even if you have a black hole where light cannot escape it, then because of quantum effects, right, you could, near the event horizon, there is a finite probability of radiation taking place. Okay, this is of low probability, but it is finite, it is non-zero, and therefore you can have this radiation, and this was given the name Hawking radiation. Now, like I said, since this has a low probability, this Hawking radiation is not very efficient, it's not a very fast process. So, but gradually the black hole will lose its mass and it can eventually evaporate, right? So that's how a black hole can actually give you Hawking radiation, right? And finally, in principle, these black holes can later on evaporate and kind of die off. But since this is a very slow process, in most cases, the black hole will not die off within the age of the universe. It would take a longer period. Next thing is what happens if you fall into a black hole. So that's an interesting thing. So the biggest problem in a black hole is what are called tidal forces. If you have tidal forces, then you have something called spaghettification. That means, say if I'm falling into a black hole, my head and my feet will feel a different amount of gravitational force, and that is nothing but the tidal force. And because of that, I will get stretched. Okay, I'll become like a spaghetti, and you'd get stretched in that way. The other effect of what will happen if you fall into a black hole is that time will dilate. That means time will move very slowly, and you could be like falling into the black hole kind of forever. Right? Do black holes last forever? No. So in principle, due to Hawking radiation, you will have the black hole kind of dying out because it will kind of evaporate with time. But like I said, this process takes much longer than the age of the universe. So that's a slow process. So you kind of may have the black hole staying on. And now we come to a very important question about what are the different types of black holes. So the typical type of black hole we already spoke about was stellar mass black holes. That is black holes which have a mass of about, this happens from like 20 times the mass of the sun. If the mass of the star is about three times more, or up to 8 times more, it will form a neutron star. But if it's even more heavier, it can fall a stellar mass black hole. It can form, if it's more than 20 times M-Sun, it could actually have a supernova blast, which would then give you a black hole. So one of the observational evidences we have is about binary systems, which actually emit X-rays as they accrete material, for example, in Cygnus X1. And you can also see it through gravitational waves. Intermediate black holes, intermediate mass black holes, these have a mass of about 100 to 10,000 times the mass of the sun. These have been detected using observations, but we do not very well understand how they form. So one probable mechanism is that you just have merging of smaller black holes which add on together to give you an intermediate mass black hole. But otherwise we do not know very well what is the physical process that actually makes things other than mergers, right? And the other very important kind of black hole is what is called the supermassive black holes. So what is noticed is that almost all galaxies, most of them, have a massive black hole sitting in the center. For example, even our galaxy, Milky Way, has a black hole of the mass of about 4.3 million times the mass of the sun sitting at the center. And the interesting part of this is that because they are found in centers of nearly large galaxies, we assume or we think that it has got something to do with the formation and the evolution of galaxies, the supermassive black hole sitting in the center. And that's what makes them interesting. There's also another kind of black hole which has been hypothesized, which is called the primordial black holes. That is, this is from the beginning of the formation of the universe. Okay, so in the early universe, probably you could have had density fluctuations, and because of the density fluctuations, you could have had primordial black holes forming. Okay, so these are the ones which formed in the early universe. So if you see the table over here, stellar mass black holes would be from this range. Location binary systems or in star clusters, you detect it with X-rays or even now with gravitational waves with the LIGO. Intermediate mass black holes have been seen in globular clusters or dwarf galaxies. We can observe them with X-rays and radio flares. Supermassive black holes, which could have 10 power 6 to 10 power 10 times the mass of the sun. These are in galactic centers. You detect them through AGN jets, stellar orbits, study of the stellar orbits. And the primordial ones, which I told you would be less than 1,000 times M-Sun, possibly could be everywhere, but it's just a theoretical idea. We haven't yet detected this. These are important because the stellar mass ones would be related to obviously stellar evolution, gravitational waves. Intermediate ones could show how the supermassive black holes, which are sitting in the center of galaxies, how do they actually grow in the early universe. And the supermassive black holes, obviously, like I said earlier, they would govern galaxy evolution and structure formation. So this is something I already spoke about. How do astronomers detect black holes given that they're invisible? So like I said, you'll get radiation. You get some kind of radiation. These ones which I'm basically talking about is not the Hawking radiation, but what I'm now talking about, the radiation in the neighborhood of the black hole. So for example, if you detect it in accretion disks or X-rays, these are around the black hole. So you have material falling into the black hole with very high velocities, which will emit in the X-rays. So there is the Cygnus X1 source, which is the first confirmed black hole, which was observed in 1971 via X-rays. You also have quasars, which are supermassive black holes in ultra-bright accretion disks. You could, a very standard method also being used, for which a Nobel Prize was also gifted, was for the gravitational influence in nearby stars. So you look at basically stars near the center of the galaxy, the galactic center, Milky Way, and you actually use that to track their orbits, to trace their orbits, get their velocities, and in turn get the mass of the supermassive black hole in the center of the Milky Way. So that has been done. This is near the Sagittarius A star, which is sitting in the center of our galaxy, right? Another very interesting method used is what is called gravitational lensing. It's very interesting that actually gravitational sources can behave like lenses, okay? So what that basically means, like a lens can bend light. If you have a gravitating source, it will bend light. If it bends light, it will cause a lensed source. So these are what are called the microlensing events. For example, these are the ones in which actually rogue black holes could be found. Another upcoming method is of gravitational waves. We know about the LIGO detectors, which actually detect gravitational waves. And they could be either caused by merging neutron stars or black holes, etc. And you have the gravitational wave detection, for example, GW150914 or GW190521. The first one is with merging black holes, and these ones are basically being detected, right? India is now building its own LIGO detector, So we'll be hearing much more about sources like this very soon. You could even have jets and radio emissions which are coming because of the accretion taking place. You could also have the presence of missing stars, failed supernovae, which have disappeared basically because they collapsed into a black hole. So the summary you can see over here. There are different ways of detecting it. There are X-ray binaries, which you see from the hot accretion disk, and you get this. And then you could also have observational evidence. Okay. Now, what observational evidence supports the existence of black holes? Like I said, motion of stars, X-ray emission from accretion disk, gravitational waves, jets, radio lobes, and Crab lensing. So, and the final one is, like I already mentioned to you, what happens inside the black hole. This is where physics actually breaks down. So, like I told you, you would have spaghettification and time dilation. So, matter and energy are thought to collapse into a singularity at this point, and this is predicted by general relativity. The infalling matter adds the black hole mass, angular momentum, and these are the things which will be added on that remain observable, and this is often called the no-hair theorem. So thanks so much. Nice talking about black holes. I hope you enjoyed that, and thank you very much. Bye-bye.